Welcome to ETEC221 lecture series. Today's lecture is lecture 3, part 1. We will talk about analog to digital converters. There are many applications in which computers, microcontrollers, or programmable logic controllers, or PLCs, must interface with the analog signals, process their values, and make decisions based on current analog values. Analog to digital converter is usually an IC chip that we use to interface between a computer and the analog device like sensors, transducers, and so on. Since we cannot convert each sample of the analog signal to infinite number of quantized discrete levels, there is always a trade-off between the quality of the digitized word and time required to complete the conversion. The performance or quality of the analog-digital converter is measured in terms of resolution. The resolution is the smallest change that can be distinguished in the analog input. Like in the case of DACs, the resolution depends directly on the number of bits, so it is often quoted as simply a total number n of output bits. However, the actual value depends on the full scale range of the analog input. So here is the definition of resolution that we will use. That's a full scale range divided with total number of levels, 2 to the power n, for n-bit analog digital converter. Once again, here is a reminder of the process that precedes actually the encoding, analog digital conversion. We're going to sample the input analog signal and we will quantize, and both of those processes will introduce certain degradation of the original analog signal. The time required to convert a single analog input to a digital output is called conversion time of an analog digital converter. Conversion time might include any other delays, such as an access time related to acquiring and converting an analog input. If defined like this, the total number of conversions executed each second is the reciprocal of the conversion time. This is very important specification that imposes a limit on the rate at which the input signal is allowed to change. As we discussed earlier, the analog digital converter takes samples of the input analog signal before converting them into digital data. The Shannon sampling theorem states that sampled data can be used to faithfully reproduce a time-varying signal provided that the sample rate is at least twice of the frequency of the highest frequency component in the signal. That's an Nyquist rate. Thus, for a valid presentation of the input signal, the analog digital converter must perform conversions at the rate equal to or at least twice at the rate equal to at least twice the highest frequency in the input signal spectrum. If the input signal is a single sine wave with a frequency of, say, 1 kHz, the sampling frequency must be fs higher or equal or higher than 2 times fm. That means 2 kHz. This will determine the conversion time of the analog digital converter at maximum Ts reciprocal value of the sampling frequency less or equal 0.5 milliseconds, including not only analog to digital conversion, but all other delays and processing time. The other specifications of the analog digital converters are almost the same as specifications of the digital to analog converters, like offset, gain, linearity, and so on. There are several types of analog-digital converters, each having its own advantages and disadvantages. With respect on how fast analog-digital converter perform conversion, we will mention several most important converters. Flash analog-digital converters as the fastest one, successive approximation analog-digital converters, dual slope or integrating analog-digital converters, and counter-type analog-digital converter. We will start with the slowest analog-digital converter. That's a counter-type converter. The counter-type is a very simple converter consisted of a binary counter, U1, voltage comparator, and the counter and digital to analog converter. When AND gate is enabled, and that means that the output of the comparator output is set high, the clock pulses are passed to the counter and counter counts up. This gate will be enabled only if the output of the comparator is high, meaning that the signal at non-inverting input, that's the analog input signal, is higher than the signal at the inverting, which is the digital to analog converter output. The later one is actually a feedback from digital to analog converter, which generates the voltage proportional to the content of the counter. The disadvantage of this type of converter is that the conversion time depends on the signal amplitude. In case of a large amplitudes, an 8-bit converter might require as many as 255 clock pulses to perform a conversion, which makes counter-type converter very slow in comparison to other type of analog-digital converter. And here is the illustration how conversion time depends on the current amplitude. For let's say for this amplitude, which is fairly high, we will start counting from 0. So the content of the DAC will be 0, and since our signal is higher than 0, the output is set to 1, the gate is open and clocks are now being counted in the 8-bit counter. As we are counting, as we are increasing the content of the counter, the output voltage increases in steps, of course. As long as this output is lower than actual amplitude that we are converting, the output of the comparator will keep the gate open. But as soon as the content of the counter exceeds the actual amplitude, the output of the comparator drops to 0, the gate is closed, and the current content of the counter actually represents coded word for given amplitude. In this case of the high amplitude, we have a lot of steps to do. However, if the amplitude is low, the counter quickly counts up to the value that is higher than input amplitude. So the duration of the conversion will be very, very short for those amplitudes. So to summarize the advantage, it's a simple electronic circuitry. Actually, there is nothing special about to design such an analog to digital converter. However, disadvantage is conversion time, as we said, depends on the amplitude of the input signal, and in the worst case, it can be as high as 2 to the power n minus 1 clocks. Therefore, it is considered to be a very slow converter. Now, improvement of that counter type comes in the form of a tracking analog digital converter. The tracking analog digital converter reduces the number of pulses required by replacing the up counter, like in previous case, with an up-down counter. The counter is not reset after each conversion. I mean, it doesn't start conversion from 0, but rather counts up or down from its last count. Now, the total number of pulses is proportionate to the change in the analog input, not to the magnitude. The disadvantage of this converter is unstable count when analog input is constant. That means that the count might oscillate up and down around that current value. So here is the block diagram how the up-down counter works. As we are counting up, we increase the content of the DAC. DAC output goes higher, and depending whether the input signal is higher or lower than that, we will set up outputs to 0 or 1, which will define whether to count up or whether to count down. So if we are exceeding the amplitude, of course we will enable counting down. Once again, advantage, significant improvement in time required to complete the conversion, and disadvantage is that the binary count can oscillate up and down from the fixed count when the analog signal is either constant or changes very, very slowly. Dual slope integrating analog to digital converter. This type of converter utilizes the integrating effect of the op-amp on analog input. When the input voltage EIN is constant, for instance positive, the integrator's output is a linear function of time, or ramp as we say, and it can be defined as Vout equals K, where K is a constant, times T. So it's a linear function of time. Slope K has a value of negative EIN over time constant RC. Now let us take a look into a typical integrator circuit that is shown in this slide. It is consisted of comparator, feedback capacitor, and input resistor R1. Now here is the switch, which has two positions. In the first position, we are bringing a sample that we want to integrate. And in the opposite position, some reference voltage, here 5 volts, will be connected to the integrator. Before we actually explain the functionality of the integrator, and I know that it's not been covered in ETEC221, let's see what we know about this circuit. First of all, non-inverting terminal is grounded, because differential voltage as a difference between potential at the non-inverting and inverting terminals must be very, very low, otherwise the output goes into saturation. That means that the inverting terminal is on virtual ground. This is a grounding point as well. If so, then the voltage IEN that is connected at the point A appears across the resistor R1. So EIN becomes voltage drop across resistor R, and using Ohm's law we can define current through it. The current will be, of course, EIN divided by R1, and it's constant as long as EIN is constant. One might argue that EIN, being a sample of the analog signal, which changes all the time, is not constant. Yes, this is actually true. However, sampling and hold circuit will keep the amplitude sample constant during the conversion. So it's justifiable to assume that this will be for brief period of time, for very short time it will be constant voltage. Secondly, if you remember, current that flows into op-amp is very, very small due to extremely high input impedance. That means that the current I that flows through R1 will flow through capacitor C1, making voltage drop Vc across it. Now, we said that in inverting terminal is grounded. If we apply Kirchhoff voltage law around this loop, you will see V out plus Vc to be equal to 0. That means that the output voltage is identical to Vc, voltage drop across capacitor. It's just that the polarity is opposite. So what's left is to establish correlation between the input current and output voltage, or capacitor voltage, because as we saw they are practically the same. Remember that capacitor charge is proportional to the voltage across it. If charge changes, that means that the voltage must change as well. So this change we will call delta Q, and change in voltage across the capacitor we will call delta Vc. If we divide this equation both sides with delta T, you will have this expression. Now you recognize the delta Q, change of charge in time, represents current. You recall that delta Q over delta T is actually by definition current. Now if you solve this equation by delta Vc, you will get this. In infinitesimal form, when delta T tends to 0, you will get derivation dVc is equal Ic over dt. You will get the derivation of voltage across the capacitor as I over C dt. To find the value of Vc, all we have to do is do integration of both sides. I over Ic is a constant, so it gets out, and integral of dt will be t. So this shows you that voltage across the capacitor is a linear function of time. Now if you substitute Vc in this expression, and you substitute current with the Ohm's law, you will get the final expression that the output voltage of the integrator is proportional to the amplitude of the input signal, considered to be constant for the duration of the conversion, divided by time constant. The output voltage is a linear function of time with a slope that depends on the current amplitude and time constant. Of course, this sign tells you that the output voltage will have a positive slope if the input signal is negative. So in this case, slope being positive will cause a ramp up linear function that has a positive slope. However, if this amplitude is positive, then the slope is negative and you are ramping down. So all we have to remember is that we have a linear rise or drop depending on the slope, and this slope depends on the amplitude. We will proceed now building our analog to digital converter dual slope by adding another comparator, U2. The comparator U2 allows the reference clock pulses into the counter circuit, which we will analyze soon, whenever the integrator output is higher than 0 volts during the EREF integration exclusively. Pulses are not allowed while input signal EIN sample has been integrated. So if you look at the schematic addition of U2, we will monitor the difference between actual integrator's output and 0. As long as the integrator's output is higher than 0, we will have high logic at the output of the integrator, which will open this gate, and the pulses will go through to point C. Here is one additional requirement, and that is that the pulses are counted only when we are integrating EREF, reference voltage. Here is the simple solution to provide that, although it's not a real one. In real life, it requires a different solution. But here is very convenient because our input signal is assumed to be lower than reference voltage. So in the first position, it will provide 0, and in the second position, it will connect EREF, which is 5 volt, considered to be 1, and the gate is open for clocks to go through. Consequently, the number of clock pulses will be proportionate to the amplitude of the integrated input sample. For a large input amplitude, it will take more time to ramp down to 0, and therefore more pulses will pass through. This can be verified by looking into the waveform of the input signal, which we bring for integration, the output of the integrator with the ramp up and ramp down, and the pulses that are going through the gate U3A. Obviously, the higher the amplitude, the higher integration voltage will be, and then when we connect to the reference voltage, the ramp down will last longer, so it will allow more pulses to go through. Unlike here, let's say, when we have a lower amplitude or when the integration is shorter, then the integrator will reach lower output voltage and it will ramp down sooner, so it will be only few pulses going through. What is important to establish is correlation between the amplitude and the number of pulses. We will now derive the mathematical expression which correlates time it takes to ramp down a number of pulses with the actual amplitude of the sample that has been integrated. And at the same time, it will give us an idea how the analog to digital converter operates. If the integration time of the input amplitude sample, here assume that EIN is negative, is T1, then the corresponding output voltage of the integrator will reach the value which we designate here arbitrarily as Vm. Vout is a linear function of time. If we want to calculate what will be the value of the output voltage at moment T1, we substitute value of T with the T1, and then this value represents the maximum voltage we will reach. Of course, it's related once again to the negative amplitude of EIN. At the moment T1, the switch S1 connects to the reference voltage EREF, which has opposite sign of the sample polarity. Now this ref will be integrated with the same RC constant because we didn't change any component in the circuit, but it will have opposite sign because EREF is positive. So then that means that we are going to ramp down. characteristic of ramping down is that it always has a fixed slope because RC are constant and E reference is constant as well. Whether we have a high amplitude of the input sample or low, the ramping down happens with the fixed slope. So you can say that this equation, V out of t, describes ramping down from the starting point Vm, when t is equal to t1, then this whole term is 0, starting point is Vm, and it lasts until we reach certain point t2, when this output voltage drops to 0. So we can write that this linear equation, which describes ramping down at the moment of t2, will get the value of 0. So substituting expression V out for the moment of t2 when it reaches the 0, and if we solve this equation by t2 minus t1, which represents the time that we will allow pulses to go through, is proportional to the input amplitude, the reference voltage, and time t1. T1, once again, is integration time of the input sample, and it's fixed, it's defined by internal clock, which controls how long we're going to integrate input sample. It's proportional to the amplitude, which is crucial, and it's reciprocal to the EREF. But EREF and T1 are constant, so this time, T2 minus T1 is proportional to the amplitude. The higher the amplitude, the longer this time will be, more pulses will go through. Now, you might ask yourself why we keep on assuming that the input sample is negative, and then because of that, EREF is positive. It really doesn't matter, because even if the input amplitude is positive, then the reference voltage will be negative. So we're going to start our integration by ramping down for the time t1, and then from that point, because we are now switching negative EREF, reference voltage, we're going to start ramping up. So when we have opposite polarity, we will have mirror picture of the one that is applicable for negative input amplitude. To get rid of the problem with the polarities, in this final expression we put EIN and EREF as an absolute value, so we get rid of the problems with polarities. But you should keep in mind that they are always opposite. So here is the final, more or less, block diagram rather than schematic of the dual slope integrated analog to digital converter. And let's quickly summarize its operation. Here we have integrator. Integrator integrates either the sample of the input voltage or reference voltage that has the opposite sign of the current sample. The second comparator keeps the gate open or closed depending on the phase of the integration. The control circuitry will allow integration of the analog input for some time t1, and then it will hit switch to EREF position. When it's in EREF position, the clocks are allowed through the gate as long as the ramping down voltage at the output of the integrator is higher than 0. During this time, clocks will be counted by a counter circuit, which is represented only with one counting stage. But in reality, you might have many counting stages. It all depends how accurately you want to present your amplitude from the digital display, from readout. Each of those counting stages will control one digital 7-segment display. So what is the basic advantage of this dual-slope analog-to-digital converter? The accuracy is high because it depends only on EREF and not on RC components or accuracy of clock pulses. In the previous slide, we verified that the time interval T2 minus T1 is not a function of RC components at all. It depends only on input amplitude and EREF, so a reference voltage must be very precise. In addition, the integrator suppresses the noise, high-frequency content. The integrator output amplitude is inversely proportional to frequency. Therefore, the high-frequency noise components in the input signal are attenuated. This property makes it useful for instrumentation systems, and it's widely used in digital voltmeters. Principal disadvantage is that it's not particularly fast, so its use is restricted to signals having low to medium frequencies. And that will be the end of lecture 3, part 1.